All right, you've heard all the announcements. I can't think of anything else to do. Any questions before we get going on today? All right. We had talked about solving a separable differential equations. We finally get to do one. Okay? Here's a differential equation. Let me get my pen set up. 1 plus x dy minus y dx equals 0. I said it was separable. Is it? Yeah. Okay, how do you do? What would be your first step?
Y dx to the other side.
Yes, I like that. 1 plus x dy. We'll be adding y dx to both sides. Okay, those wipe out is equal to y dx. Now what? I'm sorry? Divide both sides by y. That sounds like a good idea. Wipes out the y's here. And okay, you got the dy's and y's together. That's good. 1 plus x. Okay. Divided by 1 plus x. So over here, these wipe out. So you have dy over y is equal to dx over 1 plus x. Okay, and now what? I just take the root, integrate both sides. And what? And what does that give you? Natural log of y is equal to natural log of x. Now, I'm going to do something strange here. Normally, I just write a plus c. Okay? But, because everything else is in terms of logs, I want to make... Huh?
That's my question.
Yes. Let's just make this constant log c. Why not? It's a constant still, right? Okay. Now what can we do?
Log of 1 plus x times c.
Yeah, okay. The log of y is equal to the log of c times 1 plus x. You buy that? Because the log of the sum of two logs is the log of their product. I don't know if you remember that rule of logarithms.
C, so, I'm sorry. Because we're doing the plus c.
Say again?
I was writing everything.
Oh, yeah,
down.
okay.
I'm sorry.
Rather than writing plus c, I chose to write it as plus log of c. That's still a constant, isn't it?
Yes.
Okay. And the reason I did that is so I can combine these two. The sum of two logs is the log of their product. Does that make sense? Okay, you remember that rule?
But why are you
Why
throwing
do
the log
that?
in the C?
Why do the log of c?
Yeah.
So I can do this. Because that's what I'm going to do next.
Take the log.
No, exponentiate both sides. And wipe out my logs.
Like with the E?
Yeah.
Okay.
Because the log of the end of the log.
Yes.
Right. Now, see, if this gave you any pause to get there, that's where Bill and I have a big advantage. Because you see, a slide rule was always, if you're trying to multiply these numbers, you added their logs.
Yeah, I don't even know what you're saying.
Yeah, exactly. Yeah, so you see, you and your calculator. Okay. So.
I don't even write on paper anymore.
Yeah, I know, I noticed. Okay, so we're going to exponentiate both sides, and that gives us y is equal to, basically, second, c,
times 1 plus x.
got it. Okay. And for the strangest region, yeah, that's what they finally did. They went a lot more difficult pattern to get there, but it's still what they got as their answer. Y is equal to c times 1 plus x. They didn't write the plus c here. They plus log c. They wrote plus c, and then they had to fiddle around with exponentials and stuff like that, and then finally get it to that form. If you just had done that to begin with, you.
With the natural log, how would you write that you got from showing the natural log to the y equals?
Okay. All right.
I'm sorry.
Do that. No. Do that. Good question. Oh, so e to the that, e to the that.
That's what I thought. Okay.
Yeah.
So
Right. Yeah.
Well,
You exponentiate both sides, and e of the log is that inverse operations of each other. Wipe out. You just get the y, and e to the log of c plus 1, c times 1 plus x is e wipes out the log, c times 1 plus x. Okay. Now, that's not the only way to get there, but that was, to me, the easiest way to get there. And I was just looking ahead, since both of these were in terms of log, why not write my constant in terms of logs too? And it just makes the rest of the problem so much easier. Because log c is just a constant. You can write constant any way you want to. You can write 4 million plus c, that's still a constant.
you don't know what it is.
You just, yeah, you don't know what it is. Right. Now, of course, c couldn't be negative, but, you know, it won't work in the problem if it is anyway, so, okay. So, I don't think it would anyway. All right. And that's what they go into next, is the judicious choice for the constant would rather be log c rather than c. And they do put that c in absolute value bars so that allows c to be negative. And then I guess this c can be either positive or negative. It really doesn't matter. Now, can't think of anything else to do with that one, so let's move on to example 2. Any questions on that before we go? Okay. Let me clear this. Let's do example 2. An initial value problem. dy dx is equal to minus x over y. With this condition that y evaluated at 4 is equal to minus 3. Okay. Now, what would you do to solve this problem?
Get everything on the same side.
Okay, well, all like things on the same side. Okay, so how would you do that?
You multiply by y.
Okay, multiply both sides by y. That will get rid of the y's over here and get y with the dy, which is a good thing.
Multiply by dx.
And yeah, now pure mathematicians would hate hearing that, but this book actually does it that way. Multiply both sides by dx, or write this in differential form, would be y dy is equal to minus x dx. Subject to y of 4 is equal to minus 3. All right, what would you do next? Integrate. And what do you get? over 2 is equal to is what? Minus x squared over 2.
I've already put it on the side, so
What's that?
I have already put y back
Okay.
on this side, x squared
All right.
over 2 plus y squared over 2
Okay. And
equals.
you can put a plus c down here, not a bad idea. If this were not a initial value problem, I would actually put it as a c over 2 so I could wipe out my
I
2's.
was about to say,
Why not? Let's go and do it that way, okay? C over 2. Why not? That's still a constant, okay? And that means that if I can write it another way, x squared plus y squared is equal to c. And in fact, maybe we should have said that c squared over 2. That would have been a constant, wouldn't it? Okay. So this would have then been a c squared. And what would this describe? Huh? A circle, exactly, of radius c. Okay? But we do know two values here. We know when x is equal to 4, that would be 4 squared plus y is a negative 3. That has to equal c squared. So this would be what? 16 plus 9 is equal to c squared. C is equal to 5, right? Okay. So let's write our answer. X squared plus y squared is equal to 25. But that isn't a function, is it? Okay. Now, what we need to do here is go back. I know we've used it, but let's think about what that initial condition tells us. Let's draw the graph of that circle. Okay. Now, I don't draw circles very well at all. But let's just imagine that's a circle. Okay. Y of 4, so x is 4, is equal to negative 3. There we are, right? So now, for y to be a function, it has to be this part, right? It can't be this up here. Because a function, vertical line test, right? Vertical line test fails if it's a circle. You know, so it's only a half circle. This will do it. So actually, you have to include an integral. So, oh well, here's another way of doing it. Let's write this in terms of y. So y is equal to minus the square root of 25 minus x squared. Isn't that that circle? Yeah. And what's that?
it can't be positive.
And it can't be positive. So that would be probably the best way. That way, you have to specify y has to be less than 0. Or something you have to do. Writing it this way is clear. It's taken care of. Now, without the initial condition, we would have had a series of concentric circles, depending on what C is, you know. So it could be the top half, the bottom half of any of those concentric circles. This nails it, the square root of negative square root of 25 minus x squared. Okay. doesn't seem absolutely necessary, but I guess it's fair to do. Remember, way back, they also said any solution has to imply an interval. So the interval here is sort of implied to be -5 is less than, I want to say equal to x is less than or equal to 5. However, in the book, for some reason, they don't include the plus or minus 5. And seems like at one time I figured out why they said that. Oh, maybe this. A solution curve, they say, is the graph of a differentiable function. And this is not differentiable at the endpoints because you have vertical slopes there. So that's why I assume, best I can do, the only reason they leave off the equal sign there is that if it has to be differentiable, then yeah, because it was given as a differentiable function. And by definition, look at our original problem, y can't equal 0. Y is equal to 0 at plus or minus 5. So that's enough. That's enough. So that's why you have to have the open circles. Good deal. X could be 0 and is, but y can't be. All right. That leads to another issue. This one started off with y in the denominator. The previous one, we wound up putting our y in the denominator and the 1 plus x in the denominator. And in neither instance did we say y can't be 0 and x can't be -1. We probably should have said that, okay? But we didn't. And they didn't seem to gripe at us too much for not doing that. So,
Why couldn't be what?
in example 1,
Oh, in example 1.
when we wound up dividing by y and dividing by 1 plus x,
Yeah.
we probably should have written out on the side y can't equal 1 and x can't equal -1, because we did that. And of course our solutions, when you came up with exponential logs, they couldn't be. But then when we came up with a y is equal to c times 1 plus x, that allowed it again. And I'm not sure.
Before, you can't do it.
Yeah, that's so yeah, it sort of makes you wonder what you are imposing in it, which you didn't really intend. And I think that's sort of what example 3 is going to be getting at. So let's take a look at 3. Okay? Yeah. Solve this one. dy dx is equal to y squared minus 4. Where would you go with this one?
Get the like terms.
What's that?
Get the like terms.
Yeah. Okay, so how would you do that?
Divide by y squared minus 4. Multiply by
And write it in differential form dx. Okay, so you have dy over y squared minus 4 is equal to dx. All right. What are you going to do with that? Integrate both sides.
GX would just be X.
That's going to be X. All right, you did the easy
I
part.
haven't seen the easy one
Yeah.
like that.
You jumped all over it then, huh?
No,
Okay.
no, that's right.
Yeah. All right, what are we going to do to the right-hand side?
We're going to do that's a tree thing, isn't it?
Possibly, but there's a slightly easier way to do it. I think it's easier anyway.
The integration of parts.
Not quite. It sounds similar, but
Or where you make a fraction out of it.
yes, partial fractions.
Yes.
Okay. So let's do dy over, well, I can't write, so help me just factor that so I don't have to write it again. What would that give you? Y, factor that denominator. Factor y squared minus 4.
We just want to say y squared plus, y plus 2, y minus 2.
Y plus 2 times y minus 2. Okay. Now, what we're going to do is break that into, in fact, let's leave the dy off of it totally. We'll go back and put that in later. Let's just do 1 over. That probably is a little bit cleaner. And we're going to say this is a over y plus 2 plus b over y minus 2. Okay? Now, remember what the next step was.
What I did was I have a times y minus 2, b
Okay.
times y plus 2.
Okay.
And I just set them equal to 1. Solve for
Okay. That's exactly right, and here's what you're in effect doing when you do that. Because some of them can get a lot more complicated. You're multiplying everything on both sides by y plus 2 times y minus 2. Y plus 2 times y minus 2. Y plus 2 times y minus 2. Okay? And here, everything goes out but 1. Right? And over here, y plus 2 goes out, and you get a times y minus 2 plus b times y plus 2. Yeah, and that's exactly what you said. Okay? That's what you said. But that's how you got there. Okay? Make it legal. Okay? Now you do something that I found really bizarre, but it works. Anyone remember what that is?
plug in stuff that makes 1 of them 0.
Exactly. First let y equal 2. What does the left-hand side become? 1. Because it's 1 and y equal 2, it doesn't become anything else. The right-hand side becomes what? Okay, it becomes 4b. Because the first term goes to 0, which implies then that b is equal to 1/4. Okay? Now, you can either plug that in and go back before, but it's so much easier to plug in the other one, which is y is equal to -2. What does the left-hand side become? Well, left-hand side becomes 1, and this becomes -4. A, right? Which implies a is equal to what? -1/4. Okay, I don't hear well, so all right. So now we can rewrite our left-hand thing here to be the integral of, let's just write the b's first because it's positive. There it is, okay. 1/4, I'm going to put the 1/4 on the outside. In fact, I'm going to put 1/4, trying to do too much at once and run out of room. Okay, probably going to run out of room anyway. Let's put 1/4 on the outside and then put both integrals in there because they both have 1/4. The first integral is then going to be 1 over, or dx or dy over y minus 2. And the second integral, just going to have a minus in front of it, the integral of dy over y plus 2. All right. Now, what we haven't done is a plus c. And I'm not sure how to do the plus c, so I'm just going to leave it a plus c this time. You always, for indefinite integrals, do need that. And this isn't a boundary value or a natural value problem, so we sort of have to do something with that. What do we get over here? 1/4 antiderivative of dy over y minus 2. Natural log of minus 2 minus natural log of absolute value y plus 2. Now I'll put my absolute values in here in case I need them, and that's equal to x plus c. Okay. Now I'm going to need more room, so since I'm through with the things on the right hand side of the screen, I'm going to erase most of that, okay? Hope that I did everything right and I don't have to go back and find that again. If I can get some of it to erase. It's being very, very slow. There we go. All right. That took so long, I'm not going to erase anymore. All right. If it's all right with you, I think I'll go on and multiply both sides by 4. Is that okay? And maybe make that c over 4. Go back and do that. So now I've got log of y minus 2 minus log of y plus 2 is equal to 4x plus c. I may regret something there, but I'll live with it if I do. All right. Now what can we do to the left-hand side to make it a little bit nicer? Second? Not yet.
I don't know how to subtract. I don't remember.
Okay.
Why don't you just make natural log as one component?
Yeah, and which component will that be?
Y squared.
Numerator, denominator.
Yes. This will be the natural log of, just like, yeah,
Okay.
yeah. Multiplying or adding two logs becomes a multiplication, dividing becomes a, subtracting becomes a, yeah, okay. So this will be y minus 2 over y plus 2. Now, at some point here, I think we can drop the absolute value bars, but I haven't ever quite figured out what makes that legitimate yet, but we'll figure it out. And this is equal to 4x plus c. I may regret this, but let's do 4x plus c. All right, I think I'm going to have to erase some more. While you're digesting that, I'll see if I can get this to erase. Okay, it did. All right. Now, what was your suggestion before? Exponentiate both sides. So the left-hand side becomes y minus 2 over y plus 2 is equal to e to the 4x plus c. Okay? Now, that's a simple exponential of a sum, which is the same as the product. Yeah. So this would be the same as e to the 4x times e to the c, which is just another constant. Okay? So we can change it or make it c. I mean, it's just a constant. Okay. So you want to make a new name, or you see anyway, just a different c? I mean, how do you want to do it? Capital C. Okay. So let's make this capital C e to the 4x. Okay. Now, I'm going to need more room, because I think I remember how they carry this to. It's the log of C, e to the C. This is just a constant. And I'll just make this capital C. Huh?
It could be anything. So
Yeah, yeah.
It doesn't need to be
Right. Right. It doesn't, yeah.
whatever.
E to the C is a constant. So that's the new constant, capital C. All right. Now, most of the time we want to write, if we can, y as an explicit function of x. And that's a pain in the neck to want to do, because it just gives you that much more work to do. But it's still doable. Okay? So we'll multiply both sides of this equation by y plus 2. Okay? All right. Now, this will wipe out the y plus 2 here. And now we have y minus 2 is equal to c e to the 4x times y plus 2c, that's especially a capital C, e to the 4x. Agreed? Okay, I put them in odd order, but forgive me that. Now, let's get all the y terms on one side and terms without y's on the other side. So that means adding a 2 to both sides and subtracting a c e to the 4x y from both sides. Okay, somewhere it's going to pop up. So these go out. Okay. Let me erase some more. This is such a shame, because we're not doing anything all that earth-shattering here. We're just changing the way things look. And what's that? I can't hear. Okay. All right. Now this is still gotten sort of messy. So here we have y minus c e to the 4x y is equal to, this is such a pain in the neck, 2 times c e to the 4x plus 1. By that? Okay. Let's factor out a y here. And let's rearrange the order a little bit here. Well, no, we want 1 minus c e to the 4x. Okay, is equal to that stuff. And then divide both sides by this. Okay. Okay. Now, what I think I'm going to do now is erase something else. Maybe this right here. I'm long past thinking I might use anything again. Hopelessly loss. Let's see how this looks now. Y is equal to, now, I'm going to put my 2 up here. In parentheses, I'm going to reverse the order of these two. It doesn't matter. It's adding, right? 1 plus c e to the 4x divided by 1 minus c e to the 4x. Okay. Now, that's a 1-parameter solution. C is the same C. It's just written in that form. Now, that's basically what they've got on the next page as a solution, except the fact they put the 2 in front. And let me make it look just like theirs. Okay. There. That looks just like theirs now, right? They use little c, but we use capital C. It doesn't matter. Now, what we did at the very beginning was divide by x squared minus 4, right? I mean y squared minus 4. And basically what that was doing for us is meaning you can't have y equal plus 2 or minus 2, right? That makes that 0. Now, if it was plus 2 or minus 2, this would be 0, and dy is equal to that. That gives you just y is equal to 0. That is a solution for this one. I'm not sure y is equal to x and y equals 0 is a solution down here. I don't think it would be. Because if this were 0 and that 0, then these would just be. What's that?
It depends on C.
It depends on C, and that would limit your C's in some case.
One, I guess.
Yeah, if x were equal to 0. So this looks like a perfectly good solution, but we do need to specify the interval of the solution. And obviously, it could be from minus infinity to minus 2. It could be from minus 2 to plus 2, or it could be from plus 2 to positive infinity, or any subset of those, but it can't ever cross the plus or minus 2. So we don't know enough to know which of those intervals to do, so we just would have to say it's one of those intervals. Now, let's see what they mean by losing a solution. It says, now if we factor the right-hand side of the differential equation, blah, 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 we know from the discussion of critical points, and that's what I was going to suggest before. Before we did anything to this, I wanted to say, but I thought it would just mess up, this is a autonomous differential equation. There's no x on the right-hand side, right? All y's. And that would mean y had to be in region greater than 2 between.
We should have set the parameters.
Right, yeah, between minus 2 and 2 or less than minus 2.
Beginning.
Yeah, you could have done it at the very beginning, and then it was specified, okay? So the x equal plus 2 or minus 2, those would have been constant equilibrium solutions that would have been allowed had we done it that way. Doing it this way, we lose those two. The solution y is equal to 2 is a member of this one right here, because I think, like we just said, when x is equal to 0, this becomes 1 plus c over 1 minus c. And if c is equal to 0, then that would be a solution. Okay? Well, c is supposed to be arbitrary. So that's okay. There's no way you can get y is equal to minus 2 out of this one. So that's the one we lost, okay? It's an equilibrium solution to that autonomous differential equation over there. Perfectly fine. But you can't get it out of this one. The 2 you can get out, minus 2, there's just no way. It's not going to happen. So, in fact, you lost a potential solution there. Y is equal to is what they call a singular solution. It doesn't come out of, well, sort of.
If it's not autonomous?
No, this one is autonomous.
But I mean, say just in general, should you always try to get as many parameters as you can?
No, okay. Parameters depends on your degree of your polynomial, degree of your derivative, the order of your derivative. I can't say the right word. That's the first order differential equation. You can only have one parameter. Second order, 2 parameters. Third order, 3 parameters.
So I mean, like on the first one, wouldn't it?
Okay.
I guess it really doesn't.
Yeah, so y squared minus 4 denominator, start at -7 then.
Yeah, but I'm talking like any problem in general that's a first order.
Yeah, you can only have one C, and that's why we wait. You know, when we do the integration here, we wait and just put a C over here. We don't want a C here and a C here and a C there. You know, that throws in too many C's. Just combine them all to one C. Now, if it's a second order differential equation, you're going to have this a second, and you expect to. But first order, and that's all we're dealing with in this chapter, I think, is first order differential equations. That's all we're going to deal with here. So we can only have one arbitrary constant. And if we have a boundary initial value problem, we'll evaluate and see what that one is. So we won't have any then. So those C's have to be the same. But what their point was, you can get your y is equal to 2, which is, from an autonomous point of view, an equilibrium solution, which is okay. But from this answer, you can get x equal plus 2, y is equal to plus 2. You can't get y is equal to minus 2. No way you can manipulate that to give you a minus 2. So you did lose an equilibrium. That's what they meant, you lost it. So that's probably why they started us off with looking at autonomous equations. Just, you can't get the solution from it, but you can identify where your solution curves are. Okay. It's kind of a nitpicky point, but it is there. All right. Let's see, we go till, remind me. Yeah, 3:45. Yeah, I was trying to remember. Okay. Because I get nervous on Wednesdays because I have to be at the other campus. So let me erase all this, unless there's questions. Any questions before I erase? Okay. Let's do example 4. That looks fairly interesting, doesn't it? E to the 2y minus y cosine x dy dx is equal to e to the y sine 2x. Given that y at 0 is equal to 0. Now, this really feels like an initial value problem. Y is equal to 0, that's where we'll begin. All right, now, what would be your first step? Would you take the first step?
I would, no, not first of all, but if I had to, get all the like terms on each side. So,
Okay, so how would you do that?
I'd probably divide by each y.
I would say that's a good idea. Oh, both sides.
Divide by cosine.
Divided by cosine x.
Multiply by dx.
And write it as a differential like that. Okay, so e to the y's go out here, cosine x's go out here. And before I write it, can you help me write it? What's e to the 2y over y? This part right here, e to the 2y over y. Over e to the y, sorry. What's that?
He's going to divide.
Okay.
E to the y.
That's e to the y minus, now there's not much we can do to that one. That would be, let's write it as y e to the minus y. Is that okay? All right, dy. I hope I won't regret that. Now, how about that sine 2x? Can we write that any other way that might be helpful here? Okay. It's called the double angle formula.
I was doing half
It's easier. And that's, I can't ever remember if this book has those in it or not. I think not, which is a shame. But I guess they want you to remember them. So sine 2x, see if you remember this, is 2 times sine x cosine x. Remember that or not? Now cosine is cosine squared x minus sine squared x. Yeah. All right. You want a quick rehash of how that came about? Oh, you got it? Everybody? Okay. Ah, okay. And if you take that and divide it by cosine x, what do you have? Yeah. That's nice, isn't it? Okay, and then what do we do? Integrate both sides. All right. I can do that first one on the left, I believe. What's that? E to the y. Y'all are good. Okay. That next one, though, I think is going to have to be a what? What you? Okay. You said it before when you were meaning the other one. When you meant partial fraction, you said integration by parts.
Yeah.
Okay, that was it. I think that's where you have to go on this one. Okay. Now, do you remember how that works? Starts with the let. Okay. A lot of them do. And you start with a u also. Now, what you're going to do with integration by parts, you're going to have a u and you're going to have a dv. Okay?
Yes.
Oh, okay. Let u equal what? Okay? No, okay. Here's the rule here. The u we want to be something when the next step is take a du. So you want that to become simpler. And the dv you're going to integrate, so you want to keep that from getting any more complicated. So here, let the u be the y, and dv be the e to the minus.
Yeah, because if you did the other
Because-
way, you'd be
Yeah,
subtracting
this
the
one would
same
get worse.
number.
Yes, okay. So this will be your y, and dv is equal to e to the minus y dy. Always keep the d's together, okay, because you got to be integrating them. Then, what's the next step? Du
Yes.
equal, well, 1 what? dy.
Yeah.
Okay, all right. Now we integrate this side, and that gives you v is equal, and you don't do any constants on these,
E to the negative y.
with a anti-chain rule kind of
I've never done anything.
a minus.
Negative, okay, my bad.
Yeah, because we see if you did a chain rule on it, if you take a derivative of this without that minus sign, it winds up being negative. So you put the negative to forego that. Okay.
I knew that.
All right. And then the next thing is combine the u and the v. So this is equal to, now, to keep from losing it, I'm going to write down my e to the y, but that has nothing to do with the integration by parts. That's just what we had to begin with. Okay? And then we had a minus sign, because this was a minus. Okay? And it's uv, so that's going to be y e to the minus y. uv. Then we do a minus, but we add a minus in front, so that's going to make it a plus. And then you do the bottom line. And the bottom line is the integral of, only it's a minus, so we're going to change that plus back to a minus again. Ooh, too many moving parts here. Okay? And that's going to be e to the minus y dy. E to the minus y dy. The minus changed that plus to minus. Okay? Now, what do we have here? I'm going to bring down this e to the y minus y e to the minus y. And then what's the antiderivative of e to the minus y? We've already done it once. That's e to the minus y, which a minus with there would be plus e to the minus y. Right? Yeah or nay?
I just got lost you in the whole thing.
Okay.
So the formula is.
All right. You mean for integration by parts? Yeah. Integration by parts is the integral of u dv is equal to uv minus the integral of v du.
Okay.
It's really the product rule undone. Okay.
I'm just not used to that first part on the equal side of the left side.
Yeah. Now this is over here because of this.
Oh,
So,
okay.
that has nothing to do with the integration by parts. But I didn't want to lose it, so I want to carry it along. But it has nothing to do with it. That's where that came from. Where the rest of this came from, because there was a minus sign here, you have a minus here, and then this is from the UV, and this is from the minus VD.
Okay. My bad.
Yeah, okay. I think I've done the right number of plus and minuses. Minus signs are only there to trip you up. That's the only purpose they have in their whole life, is to get you messed up. All right, we've done the left-hand side. Now let's do the right-hand side. And what do we have here? I'm going to pull the 2 on the outside. What's the antiderivative of sine x? dx.
Cosine x.
Okay, almost. Minus. The derivative of sine is positive cosine. The antiderivative of sine is minus cosine.
Oh, yeah.
Yeah.
Sorry.
Okay. And then somewhere here we'll throw in our plus c. Now, I don't even know what to call that c in this case. Okay? Now, another thing I sort of want to do on this one is hang up trying to solve for y, because that looks like it would be almost a total impossibility. Let's see if they agree with me. Oh, wait, I forgot. This is a initial value problem. So we got to do some plugging in. Okay, so we have to find out what that C is. So let's plug in. When x is equal to 0, y is equal to 0. So what does this become? E to the 0 is?
Sorry, I'm just trying to catch up.
1 minus y is equal to 0 is going to be 0 on that one. Plus y to the minus 0 is?
What'd you ask?
Okay.
I'm sorry, I'm trying to write everything down.
Right. Here's our initial condition. I forgot about it. Y of 0 is equal to 0. So when x is 0, y is 0. So I take this, my proposed solution, and put y is equal to 0. And here I can't find where I wrote it now. Oh, there it is. Okay. E to the 0 is 1. And this one, I put y is equal to 0, makes the whole thing 0. Okay. Plus 1. Okay, got another 1 there. Okay. Is equal to minus 2. What's cosine of 0? 1 plus c. So what's your c? Yeah, c is equal to 4.
And all this math.
All right. Now,
Trip you up, right?
now we go and put down what our final solution is. E to the y minus y e to the minus y plus e to the minus y is equal to, that c, I'm going to put c in front, 4 minus 2 cosine x. And I'm not about to try to solve that for y. That's going to be an implicit solution, not an explicit. No way to separate those y's, isolate the y. And indeed, that's what they got, is e to the y minus y e to the minus y plus e to the minus y equal 4 minus 2 cosine x. Got it. Now,
At this point, I don't even know what we're looking for anymore. Like what?
yeah. Okay. What we were doing was solving for that differential equation.
Right?
First order differential equation, don't have a one parameter system until you put in your initial value. And that's what you're calculating. Okay? You did separation of variables outstandingly, and then simplified the first part there nicely. The second part turned into an integration by parts part. Okay? This part integrated very nicely. This one you had to do integration by parts, but you got to keep them all. So this one just carried along here, and the integration by parts produced this. Okay, on the right-hand side, remember what the double angle formula for sine is. You were able to eliminate the cosine x's, and that made it pretty easy on the right-hand side as well. Just remember, antiderivative of sine is minus cosine. Okay. So then you put the left-hand side with the right-hand side, and you have to put a plus c somewhere, so it doesn't matter that. But then, because of that initial condition, it's been so long since we had been there, I almost forgot we had it, that when x equals 0, y is equal to 0. So you come down here and put y is equal to 0 here, that gave you a 1. Y is equal to 0 here, yeah. The rest is it. And then once you figure out what the c is, go back and put it in here, and that is your answer. Without an initial condition, this would have been your answer down here. With the initial condition, you figure out what C is, then put it in, that's your answer. Now, they show in the text, always so much fun, is this is a number of those infinite number of solutions for various values for C. Some of them are all positive, some of them are this, that, you have a variety. When C is equal, when the only one that passes through 0, 0 is that one, and that would be your curve, that would be your solution. When C is equal to 4, it's going to be passes through 0, 0. C is equal to 2 is one of these down here. Okay, C is equal to -2 is probably one up here. You know? So all those are possible without the initial condition. This is the only one that catches the initial condition. And I'm tired of holding the book up, so I'll go drop it. All right.
You're saying only when it goes to 0, 0, or the pair, that's the solution.
Yeah.
Oh,
The fact that y is equal y of 0 is equal to 0, 0, 0 is the only curve that passes through there. That is your solution on this one. If you left the C there, all these would have been solutions, plus infinitely more in between. Okay? But since you know it goes through that one, eliminate all the others, and the blue line is your solution, the only solution. They just happen to show C equal 2 would not go through that. Its initial condition would have been y of pi halves equals 0. Okay, and that would have given you this curve. C is equal to 2. They didn't work that out, but that's what it is. Now, getting close to being out of time, so let me, since they take about a page to talk about use of computers, well, and integral defined function, they say the remarks at the end of section 1.1, which we tend to go over really quickly, mention that it may be difficult to use an implicit solution to find an explicit solution like this one. That's an implicit solution. Hey, don't even try finding an explicit solution, y is equal to some function of x. That is going to be almost impossible, okay? The equation 8 that we've got here shows that the task of solving y in terms of x may present more problems than just the drudgery of symbol pushing. It simply can't be done. That one. Implicit solutions such as that are somewhat frustrating. Neither the graph of the equation nor the interval over which the solution satisfying that is apparent. The problem of seeing what an implicit solution looks like can be overcome by the means of technology. They used a computer to generate these graphs. There was no other way to do it. Okay? So don't try that at home. Okay? And they start talking about the computer algebra system. If you got one, use it. If you don't have one, don't sweat it. We're not going to take it any further.
It'd take me too long to type all that in.
Oh my goodness. Then on the top of 51, if an initial condition leads to a particular solution by yielding a specific value of the parameter C in a family of solutions for first-order differential equation, there is a natural inclination for most students and instructors, they say, to relax and be content. However, a solution of an initial value problem might not be unique. Man, I thought that's what we were going for, okay? They said we saw in example 4 of section 1.2 that one has a couple of different solutions. And we saw reasons for that. And so why are we rehashing it now? I'm not sure. I think they're saying that separation of variables, which they just showed us answers before, this time we're finding our own, we may need to even evaluate those. So let's just leave that one alone. Then the next little subtopic is an integral defined function, and they then refer to Roman numeral 2 in the remarks at the end of section 1.1. Pointed out that a solution method for a certain kind of differential equation may lead to integral defined functions. In other words, if you came to this stage here, We figured out a way to do this one, that was easy. We figured out a way to do that. That was not as easy, but it was doable. But what if over there we'd have gotten something that you just can't integrate? Then the answer is an integral defined function. And you would just left that as an integral as they're showing here. Y of x explicit is some y0, even if you had a initial condition given, plus, but then you have an integral of g of t dt because you just cannot integrate g of t. It's one of those.
So the answer is?
Yeah, the answer is the integral. And then you use numerical methods to solve the integral, okay? Which probably would have been just as well if you started with a differential equation and done numerical methods to solve it. I mean,
yeah,
take your money and take the choice. Yeah, if you're going to have to anyway. Yeah. But if you got that far, and maybe it's easier, maybe you have a package that will do integrals that won't do differential equations or get bogged down with differential equations. So what they call these, if you come up with something that you cannot do, they call them non-elementary functions that cannot be integrated. If you come up with one of these, just leave it as an integral, okay? And you can even do an initial problem, value problem with it, just like they showed, where was it? Here, y0, okay? You know, that will be plus the integral. All right. And I think example 5 is going to be one of those, which we will not have time to do today. Do we? So that's where we'll begin next time. If I can find my pencil, there it is. And we'll pick up there and erase this. And let's see how far we got. Whoa, we almost made it to the end. I think you can do any of the odds that are in the back of the book, 1 to 21. Do any of the odds that are in the back of the book, 23 through 27. And stop there, because the next one says proceed as in example 5, and we haven't done example 5 yet. So we'll pick that up next time. All right, we'll finish 2.2 and move on to 2.3. Now I can say, have a good weekend, okay? All right.
I like how they put on one up, it's non-elementary.
Yeah.
Is any of this elementary?
Not that I found.
So,
okay.
I need to go back.
To elementary school? Okay.